Hello and welcome everybody. Thank you for joining this webinar today. The webinar will begin shortly and will discuss energy economy and solar heat, perspectives and best practice. This is a webinar of the IEA SHC program's Solar Academy, hosted by the International Solar Energy Society, ISIS. We are looking forward to all of your participation and also your questions later on in the webinar. My name is Joanna Costello, and I'm going to take you through the first few minutes describing the work of the International Solar Energy Society. Before we begin with the webinar presentations, I would just like to inform you about what ISIS is and stands for. The International Solar Energy Society is a non-profit, UN-accredited membership NGO. The ISIS vision is to achieve 100% renewable energy for all, used efficiently and wisely. We represent a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. ISIS works together with like-minded organizations from countries around the globe to advance the renewable energy transformation. We welcome you to have a look at our membership opportunities and join as a member. You can visit our websites, ises.org, that's the main homepage, and the membership page where you can fill out the online application form is join.ises.org. We understand that sometimes the time of the webinar may not suit people in many parts of the world. While we do try to alternate the time of the webinar to suit as many time zones as possible, we know it isn't possible for all time zones, and that's why we post these webinars on our YouTube channel. So they will be available on the ISIS website for ISIS members, and then on the ISIS YouTube channel, and on the IEA SHC Solar Academy website and the Solar Academy YouTube channel. So do have a look at them there afterwards. You are welcome and encouraged to ask questions at any time throughout the webinar, so please do ask questions. That's what makes these webinars so fun and dynamic. To ask a question, just select the questions pane on your screen and type in your question. Please specify who your question is directed to, and questions will be addressed after each of the presentations. We would also like to encourage you to use the ISIS discussion forum on LinkedIn to continue the Q&A and the discussion even after the webinar has ended. A special thank you to the IEA, the International Energy Agency's Solar Heating and Cooling Programme, the IEA SHC Solar Academy, for the organisation of this webinar. I will pass over to the webinar moderator, Gabrielle Ruiz, who's the project manager at CREM and also very much involved in this task of the IEA SHC. Gabrielle will give you further information about today's agenda, the program, and take you through the webinar step by step. Wishing you all an enjoyable webinar, and I now hand over to you, Gabrielle.
Thank you, and hello everybody. So my name is Gabriel, and we are pleased today to welcome two speakers in this webinar, Sebastian Herkel and Martin Joly. This webinar will last for 1 hour and 30 minutes, and it will be split, I would say, in 3 parts. First, a very short introduction made by Sebastian Herkel, and then we will have first presentation session by Martin Joly. The second presentation session will be held by Sebastian Herkel again, meaning that after each presentation session, we will have a question and answer time, about 10 to 15 minutes. So please just let me know about your question using the question box as it was introduced by Joanna earlier. There we are. Then first to speak Sebastian Herkel, maybe some words about him. Sebastian is a department head of energy efficient buildings at Fraunhofer Institute for Solar Energy Systems, which is located in Freiburg, Germany. His works are within the field of applied research in building, energy performance, and renewable energy systems. And within the IEA Task 52, he's presently the leader of this Task 52, and his focus is on the scientific analysis of building performance and technologies for integration of renewable energy buildings in buildings. So, Sebastian, please have your introduction. The floor is yours.
Thank you. First of all, I would like to say a few words about who is IEA SHC. SHC stands for Solar Heating and Cooling Implementing Agreement. And you see on the slide that we have quite a broad distribution worldwide. And what we have developed in this program within this year, that we developed a new so-called Solar Academy. And the idea is to transfer a little bit better the R&D work we are doing in this implementing agreement, and to bring it to a broader audience. And this series of webinars is one of these effort to distribute and to share our knowledges. How you can participate, it's hosted by ISIS, as Joanna told already. And the video package, there are really shown some. First ones you can see from the last year's Qatar Green Expo, and we have other ones from the former talks this year. And we have as well the possibility to have national days or on-site training. And if you like to know a little bit more about this whole program, you can address to the website of IASSC.org, and as well we have some social media running. But coming forward to what we like to talk about, it's the outcome of a working group who worked for the last 4 years, and there were two main questions which were really driving us. And so the first idea or the first topic was really to help consultants, utilities, and urban planners to better understand, okay, what will be the role of solar thermals in future energy systems and how to plan them better. And as well, to have not a forecast, but to develop scenarios to better understand how solar energy is running in a more, let's say, electric dominated energy system. And we had in the last years quite a change on our energy system, and that definitely has an impact as well on solar heat. And to get a better understanding what might be happen in the future, that was one of the key questions we like to answer. Therefore, we have split today our presentations in two parts. The first one you will hear now by Martin Joly. That's about near future developments, how to plan better, how to understand which costs do we actually have, what are the actual economics of solar heat. And the second talk I will give is about, okay, what might happen looking at different scenarios. So I can hand over now.
Thank you, Sebastian. So let's introduce Martin Joly, who will then be the first, I would say, speaker for this presentation. Martin Joly is currently the project leader in the R&D department of Sohan SA. Sohan SA is a top Swiss company specializing in advanced building energy engineering. The main area of expertise of Martin is building physics and advanced materials for solar energy conversion. And within the framework of the Task 52, Sohan is leading subtask B, meaning we have subtask A, B, and C, and you will see it. Subtask B dedicated on methodologies, tools, and case studies. Martin, the floor is yours.
Thank you, Gabriel, for this nice introduction. My name is Martin Joly, and today it's my pleasure to be here and trying to disseminate some of the results we've got during this task. So the subject, as it was introduced, we were dealing with solar thermal energy system, and my presentation today will show you some of the work we realized concerning the benchmark, the methodology, and some best practice example. The work I will show you today is, I'm the speaker to present this work, but it was managed by a lot of people. You can see here the logos of the different people and institute involved in this work. So the motivation first. So in the world, there is a huge amount of energy which is consumed in urban area, and in this same area there is as well a lot of solar energy incoming. And the idea is quite simple: is to collect this energy to provide energy in urban area in order to increase the amount of renewable energy. The idea of this task is to give inspiration for urban actors to consider solar thermal as a reliable, efficient, and eco-friendly technology to meet future requirements. But how to do it? So my presentation will try to answer to this question, and we will focus on 3 points. So how do we answer to this question? First, we made a survey, and from this survey we made a classification and a benchmark of the main economic and technical figures. Then I will present a methodology we developed and his tool that could be used to help stakeholders at the beginning of a project to integrate in a good way solar energy in the project. I will end this presentation by showing a couple of best practice examples we analyzed during this task. Determination of in this task, we collect the data of 46 systems, existing one through Europe, and especially from Austria, Germany, and Denmark. You can see this energy system here, and the question was first how to classify it, and then extract the data collected from this existing example to make a benchmark. So first, the classification. We distinguish two main class of solar energy system. First, the solar assisted heating of individual building. As you can see here, each building is able to produce and store energy in it. There are no links between the different buildings. The second class we distinguish is the solar assisted heating of multiple buildings via a thermal grid. So as you can see here on this picture, there are examples where the buildings are not alone with the energy system, but are involved in a common energy system in which we want to add solar energy in order to increase, for example, the ratio of renewable energy in it. So here on there is many options to integrate solar energy in such energy system. Here on the left, you have a centralized thermal collectors linked to a centralized energy tank, and this energy is distributed to all the buildings, and the building itself do not produce energy or store energy. They are completely dependent of the thermal grid. The second example, we have as well a common storage system, but the solar production can be distributed on each rooftop of the buildings. Here, a last example where both solar collectors and energy storage are distributed in each buildings. Looking a little bit more in details, in the solar assisted heating of the individual building, we distinguish three subcases. The first one is individual houses that use solar energy to produce domestic hot water. A second, which is the solar combi system for single family house as well. In this case, solar energy is used to produce domestic hot water, but as well to produce heat for space heating during winter time. The third type of individual buildings, it's the solar combi system in multifamily house. So a brighter, a huger amount of dwelling. For the solar assisted heating of multiple building with the thermal grid, we distinguish two cases, which are the solar block heating. In this case, the solar collector are roof mounted. You can see here on the picture. There are different kind of different solar installation on rooftop here. And we distinguish another case, which is the solar district heating, in which it is the ground mounted collectors. So it can be like this, with a huge amount of solar collectors in fields linked to a solar district heating system. So to sum up, in this classification, we considered 5 different classes of solar energy system. The first one, solar domestic hot water for individual houses. Then the solar combi system for individual houses and multifamily houses. And the two last connected to the grid, which are the solar assisted heating of building blocks and the solar assisted heating of urban quarters. For the two last one, we considered the diurnal or the seasonal storage in the survey. Now I describe, I'm over with the classification. I will describe the results we get with our survey and the benchmark we were able to produce from the technical economic data we collect from this example. So first, the boundaries of our benchmark. So solar energy doesn't work on its own. It is always connected to another source of energy, which can be oil, gas, or wood. Let's say other conventional heat supply. This conventional heat supply is not included in our benchmark. What is included in this benchmark? It's only the solar loop, included the solar collector and the distribution system and the storage. The storage can be shared between the solar collectors and the conventional heat supply, but it is considered in the benchmark. What are the key figures we collected during this survey? So on one side, we collect energy and technical data, and on the other side, the financial data. So on the technical data, for example, we collect the kind of solar collector used, the kind of technology used to store the energy, the typical size of the solar collectors, the typical volume of the storage, or the specific storage volume, which means the number of liters per square meter of solar absorber, but as well the typical solar energy yield and the typical fraction of the different system. For the financial data, we were able to collect the specific cost of solar installation ready installed, but as well the specific cost of the material itself, which means, for example, the solar collectors or the cost of the storage itself. Another parameter interesting to know was the cost of the energy itself distributed, which means euro per kilowatt hour distributed. You will find on our website all these economic figures, which are quite interesting, and I will go through some of important figures. So here, for example, you have one of these output of this this study. So here you have the specific volume, storage volume, as a function of the energy system. So here you have the different energy system described from our classification, and you have the specific volume, the mean needed volume for each energy system. You can see, for example, on this picture, that for diurnal storage, this is this one, you will need much less specific volume than for seasonal storage, which is quite evident, but you will be able to have an idea of the amount of volume you need. This figure shows you the specific cost, euro per meters cube, as function of the storage volume needed for your installation. On this figure, you can see four curves, three curves, and these three curves are linked to the technical storage needed for the energy system. So in red, you have the cost for the storage for a domestic hot water tank. Here in blue, you have the curve for the pressurized thermal tank storage, and here in green the cost, specific cost for non-pressurized thermal tank. Last slide of the benchmark. Here we plot. We were able to derive a function to know the specific solar thermal costs as a function of the solar thermal corrector area. And you can see here this nice curve from which you can derive from the square meter you have the price of your installation. There are two curves. Red is the roof-mounted system, and in blue it's for ground-mounted systems, both with diurnal storage. This is it for the classification and the benchmarking. I will now describe the methodology and the tool we developed during the task to integrate the solar energy. Because in parallel with the first, with the classification and benchmark, I just show, the question is, you have the value, but it's not really clear which question and which is the central, the crucial question you should ask at the beginning of a question. at the beginning of a project to go in the right direction, let's say, to integrate solar energy. The methodology we develop, it's a 4-step method. So first, the idea is to determine the boundary conditions, then to pre-select an energy concept. Third step is to calculate, to quantify solar indicators, such as solar fraction, cost evaluation, or CO2 reduction of your energy system. And then there is the 4th step, which is a refinement step, where you can check the influence of some parameters or compare different scenarios. The first step is to determine the boundary conditions. So when you have a new project, there are many questions. It can be political, technical, economical constraints, question about the temperature of the network, of the needs, or for example, do you have it is a new building or refurbishment, things like this. And the idea is we develop a decision path, which is in fact a decision tree, to link this boundary condition to propose to pre-select an energy concept. So from your boundary condition, this decision tree can lead you to these 5 energy concepts that we develop in parallel in our benchmark. So here, the 3 individual houses, and here the 2 solar energy system connected to district heating system. Once you have pre-selected this energy concept, the idea is to determine solar indicators and trying to quantify it in order to compare different scenarios. And for this, we develop an Excel tool that I will show you. So I will not go into detail of this tool, but let's say it's a really easy and straightforward tool. Here in yellow, you have the input you should give to the tool, and in red, the output of the tool. It's really straightforward. The input of this tool is basically the amount of solar square meter you can put on your building or or ground-mounted system, and the square meter of heated floor area you have. If you have more than one building, the same. You use the total amount of solar thermal area and the total heated floor area. From our benchmark, we were able to derive from the surface and the energy concept the amount of energy you can produce. From this heated floor area and using the Tabula web tool, we were able to estimate the amount of energy, which amount of energy is needed as function of the building. In this example, it can consider single-family house, multi-family house, or apartment block. Using only these 2 inputs, we were able, from our benchmark and other data, to derive following outputs. So first, you are able to know the storage volume you will need. You can know which solar fraction you can target as function of the surface of collector area. Then you can have an idea of the cost, for example, the storage, and the solar thermal system itself. You can derive as well the cost of energy for solar thermal. And if you are connected to a non-renewable energy, you can calculate the saved emission of CO2. Finally, the tool will give you an estimation of the pipe lengths you should target to reach the national mean heat density of your country. I will end this presentation with describing the best practice example we studied in this task. So you can see here on this map the best practice example considered. So from Switzerland to Germany, Austria, Denmark, and Sweden. For this best practice example, the first idea was to collect the technico-economic parameters of this installation, but it was not the only goal. The idea was as well to understand which decision steps was applied at the beginning of the project, and which tool were used, and what was the design process to obtain the retained solution. In this work, we also focus on the barrier and the success factor that led to an energy concept, including solar energy. I will go quickly through the existing base practice example, but you can download it here from the task 52 web link here. So first, the solar district heating with seasonal storage in the city of Dronninglund, Denmark. So in Denmark, there are traditional using district heating networks, which has with production in the suburb, and the heat is distributed in the city. You can see here in this example this huge amount of solar energy collectors connected to a big water tank that can provide 50% of the need are covered with solar energy. Another example, hybrid solar district heating in the city of Tars in Denmark as well. In this example, it is quite interesting to see that two kind of solar thermal technology were used. You have here the flat plate collectors to preheat the water, and then you have the parabolic trough collectors to reach a higher temperature value as they want to reach 95 degrees Celsius. This solar installation is connected to the return pipe of a combined heat and power plant. The solar-assisted urban quarter of Salzburg, Lehen, in Austria. So here you have the example of a new residential buildings. These new residential buildings are linked to an existing solar district, district heating system, and the solar installation are mounted on the rooftop, and all these 13 installation feed a common storage in order to provide energy to the buildings. This installation is able to provide 25% of energy with solar energy. Same kind of installation, the solar-assisted urban quarter in Freiburg, Gut-Leutenmatten in Germany. Once again, the solar collectors are roof mounted, but in this case, it's not centralized energy storage, but it's decentralized energy storage. It means that in every basement there is centralized there is a storage. And applying a sophisticated hydraulic system, the energy can be exchanged between the different buildings and between the buildings and the existing district heating system. A very interesting example is the solar-assisted residential area of Baldaheberg in Kungsbacka, Sweden. For this example, which is a totally new residential area, they built a new solar district system. Here you have the wood pellet heat production with evacuated tube collectors and a primary steel pipe system. This piping system distributes to 4 substations. This substation, the water is preheated by solar thermal as well. And there is a secondary heating network that distributes energy to passive house. And this is interesting to see that for this low temperature secondary network, they use plastic PEX pipe with water distributed at 60 degrees Celsius. I will finish my presentation with the 2 last Swiss case studies. So here is the solar-assisted mountain holiday resort Recka Feriendorf in Nates. So you have the 50 flats connected to a common system. This one is quite sophisticated, as it uses hybrid solar thermal power, PV solar collectors, and heat pumps connected to borehole. Using seasonal storage through borehole, it was able to reach the impressive amount of energy of solar energy of around 65% of energy covered by solar. Another really interesting example is the solar-assisted apartment block of La Cigale in Geneva. So here you have the two blocks, which first they made the refurbishment of the envelope in order to decrease the thermal need of the buildings, and they add a system. So it's roof-mounted unglazed solar collectors connected to heat pump and latent ice storage, which is quite advanced system. This system, around 65% of the energy can be covered by solar. This is the end of my presentation, and I will go through the main conclusion. So first, I show you the benchmark and the methodology, and in our opinion, the work managed in this task could be really useful for stakeholder during the pre-project phase of novel project. It can provide quantified indicators for solar from basic input, and this survey includes diurnal or seasonal storage benchmark, and it is adapted to Central European countries. You can find the deliverable, so it means the classification, the methodology, and the tool on our website. For the best practice example, it is interesting to see that economically viable solar thermal system exists, and there is very diverse technical solution to integrate solar thermal energy. But what we can put into evidence that in every project we analyze, there is always a strong willingness at the beginning of the project to integrate solar energy. Once again, go on our website to download the leaflet, for example, and the technical report of all the best practice example with a lot of technical data. Thank you all for your attention, and I would like to thank the Swiss Federal Office of Energy who make the funding of the research, and all the colleagues and institutions who contributed to this work.
Thanks, Martin. So let's open maybe like a 5 minutes question and answer sessions. I could collect some. I think I would try to ask you maybe 2 questions, Martin. The first one is dedicated to the, I think, related to the use case in Sweden, where apparently you said something like there is a continuous drop in solar thermal markets in Sweden. I don't know if you remember about any input on this, or if you have any more precisions.
You said about the solar drop in Sweden?
Mm-hmm. A drop in solar thermal market. That's solar thermal, or maybe it's a bit more general than only Sweden. I don't know if you have any input on this.
So I'm not able to comment this question, especially on Sweden. But here on the slide, you have the contact of the guy that made this case study. It is Martin Anderson. Feel free to contact him. Here you have his address, and it is the Chalmers University.
Okay, thanks for this. I think this is the right, as you said, the right address to ask a question about typical questions related to Sweden. Maybe another short question, if you can answer it shortly, coming back to the methodology. Could you maybe come back on the link between the decision path and the, I would say, as you said, the table, like a calculation tool?
The link between the decision path and the tool?
Yes, and the calculation tool.
So here, mainly the methodology, there is these 4 steps. So first you have the boundary conditions, and in the task we made a decision tree. So basically, you ask a question and you answer yes or no, or for example, is there any existing solar heating district to proximity at in your region, and things like this. And the idea from this boundary condition and answering a set of questions is to link this boundary condition to an energy concept. And this energy concept are the one we made in the benchmark. It was the first step. So the first step, the idea is to pre-select an energy concept if you have no idea in the direction you want to go. And the second main step of this methodology is helped by an Excel tool. And the idea of this Excel tool is to feed it with the energy concept you target, the solar area you have, the heated floor area, and this tool can provide you and quantify the solar fraction, the cost evaluation, or the CO2 reduction. And here it is a very straightforward Excel tool. Here you have a print screen of this Excel tool with the input and the output that I described before. This Excel tool is not available yet on the website, but it will be available when the report will be accepted.
Thanks, Martin, for these answers. What I propose is now to switch to Sebastian's presentation, because I think I received some questions already related to price, to competition between solar heat and solar thermal and solar PV. So I think it's maybe better than Sebastian starts with the presentation and take the questions for afterwards. Sebastian, if you like to start the presentations, the floor is yours.
Yeah, thank you very much again. What I like to talk about is about scenario analysis on this future role of solar heat, and this is work mainly done by a colleague of mine, Andreas Palzer, and maybe more important of Brian Mattison and Kenneth Hansen from the Aalborg University in Denmark. So now I'm waiting. I have some issues on, yeah, okay, here we come. Good, so content of my talk is split in two talks. One is a scenario which is addressing 4 different countries with the same methodology, looking at systems in Austria, Denmark, Germany, and Italy. And the scenario is always addressing a high renewable scenario. And what do we mean with a high renewable scenario? Means that we will reach for at least 80% reduction of CO2 emissions, and maybe even with a goal coming to a 100% renewable-based energy scenario. And then we did a solar thermal analysis looking at marginal impact, looking at the solar potential, which is, I think, a key question. Okay, well, how could be is the potential for markets, and as well, okay, what impact do they have? And having sensitivity analysis, okay, how important are cost reduction and these kind of things. And then as a second part of this presentation, I would like to go a little bit more in depth look at a scenario in Germany and draw some conclusions. So what is a scenario? And a scenario is a calculation of a techno-economical potential, and that means cost optimal systems under given boundaries, and therefore it's not a forecast. You cannot really forecast. That's the glass bowl you're looking in, but you can give some boundary conditions and look what will happen if you apply these boundary conditions, and that is what we have done. And so the analysis of the role of solar thermal concepts in future energy systems, including sensitivities analysis regarding cost developments, national and international system integration, and influence of climate change, which we didn't address, was the main goal of our scenarios. So what you see on the next slide is maybe very small. The 2 different models we used in our work in the last 4 years. The one is what I will talk about, these 4 countries. It's energy plan. And what you see is that you always have inputs. So you have a demand regarding electricity, regarding cooling, regarding district heating, regarding industry, regarding transport. And that's one of those key features of all these models, that you are not looking only into heat of buildings, but you're looking importantly as well, how are these interactions between these different sectors of the energy systems, and how does these interactions have an impact on the development of future energy supplies. So in addition, you have different capacity, storage, transport included. And what you do then is do an hourly simulation which is optimizing the costs due to the merit order. And that is what Energy Plan is doing. And a little bit different approach is what we have done in Germany with a model called Renewable Model Germany, D for Germany, Deutschland. And what you see here is as well a picture of the overall energy system. You see here on the left side, it's the one, okay, the sources here up here, the renewable resources and other fossil energies. Then you have the different electricity production. You have here in gas turbines, for examples. You have included power to fuel technologies. And what you have in really detailed way is different heating systems which were part of the model. And what we're looking then within the calculations is looking, okay, how could be the cost optimal path for a transformation of the existing energy system looks like, and from that out we can derive some figures what is the potential for solar energy. Going ahead to the first one. So Martin just explained these 5 typologies, so single family houses, multi-family houses, block heating, that means a small group of buildings, and then these 2 large solar district heating system, one with small storages and one with seasonal storage. That were the 5 ones we have addressed. And then how does a scenario looks like? So you start with the existing situation. In 2010 was our reference year. You have to calibrate it, and then you can do looking, okay, what happens if you simply go to 2050, a little bit change in climate or whatever, but you don't change anything. And then you can apply different measures and look, okay, how will these measures, which will be the effect of these measures on the overall energy system. So first thing is heat savings. Second point was applying district heating. Then looking, okay, what happens if you change, for example, from gas boilers to heat pumps? And then if you introduce a biomass. And then as a second larger steps is looking, okay, what will have, for example, the impact if you change the transport towards full electricity? That will have some impact, that there will be less electricity, for example, for heating purposes in heat pumps. And that might have an impact on the amount of solar energy which will be in the system. And you can look at it as well on the industry side. And for sure, it's a big difference on the CO2 emissions, whether you have a renewable-based electricity supplied or not. Okay, so that's the principal method, and where we have looked at mainly are these 5 highlighted ones, and I will select a few outcomes out of this full analysis. So what the typical outcome of such a study is, you get a primary energy supply, and you see now the 4 countries, Germany, Austria, Italy, and Denmark. And you see, looking at the primary energy supply, it started with 2010 with about 50 megawatt hours per capita and year. And it goes down to, let's say, 25 megawatt hours per capita per year with this high renewable scenario in 2050. And what you see as well is the expected split of different technologies in these energy supply, looking at primary energy. And what you see here, for example, that the split of solar thermal is quite a small one. It's in the same range like geothermal, and I will come later on, okay, looking, okay, why it's in that range, and that was, I think, the main question we have addressed. Or what you can see actually here as well, if you go into this 2010 scenario of Denmark, you see here you have quite a high share of other, that's mainly waste heat, and that's due to the fact that most of the district heating in Denmark, which covers more than 50% of the buildings in Denmark, is based on waste heat. Then you will have the same kind of scenarios looking at the CO2 emissions, and you see with it in this high-res scenario for the 4 countries, you have really a strong reduction in CO2 compared to the existing situation. So the analysis method is first looking at marginal impact of solar thermal. That means that you add to the existing system 1 terawatt hour of each concept and looking, okay, what will happen then? Then the second step of analysis is looking at the potentials, where I put my focus in this speech, and looking on what we call penetration. That means the amount of buildings which has installed solar thermal installed. So in the first range is saying, okay, 20% of the building have access to solar, and in the second scenario we have 50%. So coming back to this solar penetration, so if you have only 20% of the buildings connected, then that we call 20%, and for sure it's understandable if you have a higher share of buildings connected to a solar thermal. For sure you have in general a higher share and a higher potential. Looking at these marginal impacts of this high-res scenario. And what you see here, that one of the main outcomes is what happens if you add these 1 terawatt hour of solar thermal. There's quite a strong impact mainly on the biomass. So if you put in solar thermal in the system and increase it by 1 terawatt hour, it will mainly replace the biomass. And that's true for all these 5 types of buildings or solar systems. So you have here first the small systems, and you have here the district heating systems, and you see on the smaller side you have a bit higher substitution than for the large system, and you can see that for sure, okay, because you have a little bit more sun in Italy compared to Denmark, that the change is the highest in Italy relative to the other countries. So what we see is if we put in this high renewable energy system more solar thermal in, it will mainly replace a bit the small heat pumps, and therefore we might have a little bit less flexibility. And I think that is one of the key outcomes that we see, that it will be mainly a substitute for biomass. And I think what an important boundary condition in the calculations is that the biomass potential, which is the limitation, was quite high. So compared to other studies, it was assumed that there is a potential for import of biomass. Let's say, example given Denmark from Sweden, where definitely there is quite a huge amount of biomass available. So coming to the solar thermal share of heat and the heat himself and the square meter, what we see out of these scenarios. And if you go into these graphs, you see here, that's the solar collector area areas in million square meter for Germany. And you see, okay, if you put it now in the market, if it would be feasible, yeah, then there is a potential relatively high, because we still have this high energy demand, and this amount of potential heat production by solar thermal will go down, because for sure in this high renewable energy system we will have less demand. Yeah, so that is one part that we will have the main potential here in these individual houses, some in the district heating, and that's the overall potential if you look at the installed area. If you look at the energy produced, that's about 15 to 60 terawatt hours per year, and that is in between 3 and 11% of the total heat production, which might come out of solar thermal, and the 11% corresponds to the assumption that we will have 50% of the buildings connected with solar thermal. If we say we are a little bit more conservative, saying only 20% of the building, for sure, this amount of energy will only be 3% of the total heat production. And if we go through the countries, you will see we have a not that much higher potential in Italy, and that's due to the fact that the potential of energy demand reduction in Italy is still quite high. If you compare, for example, insulation levels in Italy is a little bit less compared to what you see in Austria and Denmark and Germany. And you can go through the figures and you see the pictures more or less the same. There's a little bit for sure an impact of the electricity system, and that is one of the reasons why we have slightly small differences in the pictures in the different countries, but in general the figures look quite similar. Then if we look at the total solar thermal share, so the amount of heat we will see, then you can see if you have, let's say, a mix of assuming 35%, and look over all these scenario. If you go this blue line, for example, for Germany, assuming 35% of the buildings are connected, with these different scenarios, you might increase it. And then if you are going in a very high renewable energy systems, that means you have a huge amount of renewable electricity available. This share will go down. And what you see, Denmark is a little bit different. It's more stable. And Italy, you see, have in principle in this whole scenario the highest potential share if you go for these 35%, and that's due to the availability of solar irradiation. Looking at some impacts, what do we see? I think it's hard really to go to all these figures here on the right side. What we see that compared to biomass, or the impact of biomass, if we have these higher amount of solar energy in it, that could be reduced relative by 2 to 4%. If you have not changed your electricity system, and you can reduce it by 1 to 2% if you are in these high renewable energy systems. And for sure, the reduction, because you already are quite low, are going down if you are moving towards these high renewable energy system. If you look at the CO2 impact, it's about 5 to 1.5% before the high renewable, and that is definitely is one of those things where the two what scenario studies we have seen differs, and that's as well a conclusion out of our work that for sure given boundary conditions have a strong impact on the outcome. But we see in this study from the colleagues from Oberg University that these low reductions or the reductions are quite low if you go in this high renewable energy scenario. And you see, especially if you go here in this district heating, the calculations show that only in Denmark you have a good positive impact, and they have some doubts about to have a good impact in the other countries. Okay, I will switch now to the more detailed scenarios we have done in Germany. We have used these remote model, and it's important to understand that we have included the electricity generation, the fuels, so power to gas is included, the mobility sector, the heat, and as well the processes in industry and the tertiary sectors. And the goal is to develop a cost optimization transformation strategy to reach this goal of carbon emissions of by 80% and beyond. And if you look at the German situation, that are the carbon dioxide emissions in the past. So it in this graph it ends in 2014. And you see in the blue line that are the agreed reductions we should achieve due to the Paris climate contract. And what we have done is really a calculation year by year until 2050. And what I will show you are different scenarios for the year 2030 and 2050, and what will be the impact on solar thermal. So we have looked on 6 scenarios. The first one is saying, okay, we have the goal to reduce it to 60%, which is not sufficient regarding climate change. And then you see increase to 75, to 85, and to 90%. And then we made an analysis, okay, what will happen if the solar thermal will not go as much down? I think we have a reduction of our cost assumed down to, let's say, 350 euro per square meter ready installed, not for the full system, but for the collector side. And the second scenario is looking, okay, what happens if you have this huge amount of biomass available and the same settings regarding the share of mobility in the future system as in the other study. Looking at this scenario for the heat, and you see the amount of energy, sorry, I forgot here the caption. And you see for the heating supply, the green ones are those ones which are related to district heating. The red one is gas boiler or oil boiler, and the blue one are the direct electrical or heat pump supplied system. And you see, the stronger your reduction goal is for 2050, but measured in 2030, the higher the share of the electrical systems will be, and the lower the share of gas will be. That's very simply, and oil. And as well, you see the amount of solar thermal, that is the smaller one you see here, is the higher your reduction is you're looking for. And for sure, if you compare here this 85% reduction, same boundary conditions, and if you have a little bit lower cost reduction, well then that has for sure a strong impact. You see, it's about 15% less in this scenario we have calculated. And what you see as well, we have still quite a share of district heating. If we go now to the relative shares, you see it once more. We will have in 2030 here in this scenario a share up to 3%, which is cost optimal. It doesn't say anything about how the real market will evolve. It just says, okay, under the given conditions, what would be techno-economical potential. Okay, going ahead to 2050, which is our goal year, and you see there a lot of things has changed. If we say, okay, this 85% is the scenario where we have to go for the in order to treat with climate change, you see the remaining gas and oil boilers are very small ones. And as well, what's included here, and that is what I forget, is there's as well the biomass boilers included, because if we look at least the German situation, the biomass available is limited and have to be used mainly to produce fuels for industry and not for heating. Yeah? You see a huge amount of share of electrical system, but you see as well a reasonable share of solar heat, which is in the system. Okay, and you see, and that's important if you compare it to the study the Danish colleagues have done. We are in the same range, maybe a little bit higher in the study we have done in Germany, but the outcome is comparable, and that's a good justification that we are on the right track regarding our stuff. And having, I think it's one of the last slides, looking at the installed capacity we see in our scenarios, for sure it's increasing depending on our goals, and the capacity is changing in between, let's say, 60 to, in this very optimistic scenario, up to 160 gigawatt. And what you see as well, if you don't achieve the cost reduction goals we have to achieve, then for sure solar thermal will go down, and so solar thermal is definitely in competition with other renewable solutions. So coming to the conclusions, we see definitely that solar thermal will play a role in future energy systems, but maybe not that much as some of the solar heat community have expected. The second point is that the energy system design is crucial regarding the outcome of the solar thermal feasibility. So hydrogen or electricity as a main carrier, and you see the potential is between 3 to 12% of the total heat production. And what we see especially that solar thermal could definitely ease the pressure on scarce renewable resources as biomass. And for sure it will be in a competition regarding other solutions to achieve these high these CO2 savings. And district heating, we have a good potential, but it might be in competition with waste heat. Okay, I have some issues. Okay, we have reports available. Martin Joly mentioned it already. And for sure, it's still in the progress, so not all of the reports are yet available. So if you don't find a report you're looking at, please come back, let's say in 2 months, and you will find additional one. So that's for it, and I can hand over now to Gabriel.
Thank you, Sebastian. Thanks a lot. We received some very interesting questions. Unfortunately, time is a bit short, so we have like 10 minutes for some questions. I would say that the questions that I got are related to your scenarios. Some are also related to solar heat price, others to the solar heat in the industry, and some about the technology, the solar heat technology. For sure, we won't have time to address them all, but maybe about scenarios. There was one remark about the high share of biomass. Asking the question is, what are the source of this biomass mainly? Because it's quite a high share. How do you see what's behind this biomass term?
Yeah, it's different if you look at the study done by the colleagues in Denmark. It's quite a lot of wood you see, as well other the typical resources you have in biomass. If you look at the study we have done in Germany, we have limited it more or less to the amount of biomass we have already. So it's corn, what we have in Germany, and it's wood. I think that are, and raps, so rapeseed, that are the key resources. To look in detail how these resources are allocated, it should be in the report, and if not, I would like to ask for private communication.
Okay, thanks. Maybe a question about solar heat price. They're all going a bit to the same directions, but I would say two main axes. The first one is how solar thermal heat price can compete with low price fuel, like such biogas, coal, etc. And I think we addressed this in the task. So basically competition between solar thermal cost and other fuel costs. And then the second question is, I would say, the competition between solar heat and PV, of course. So I don't know if you, Sebastian or Martin, can say a word about these two competition factors in terms of costs.
Yeah, I can try to do it. I think what you see that the actual cost of solar thermal are starting, let's say, around at 1,000 euro per square meter if you go for the small systems, and you are going down to let's say 200 or whatever euro per square meter. The exact data you have to look at the report of IE Intake. And if you look at, so you have big price differences. And if you look at the levelized cost of heat, I think it starts around 15 kilowatt euro per 15 euro per megawatt hour. No, 150, yeah, and it goes down to, yeah, let's say 35 euro per megawatt hour in the large Danish systems. That's the actual situation. And because we have seen that there are, if you look, for example, at production cost for a collector, that's, let's say, in between 70 and 100, 120 euro per square meter. And if you look on the resale prices and the prices for already installed collectors, there's quite a huge span in between, which has to do with operation and maintenance, which has with selling costs. And there is another, a little bit newer task on especially the cost share within the solar thermal system. That's task 54. And there is a report available as well on SHC where these levelized cost of heat are. That's solar heat worldwide by IE Intake from Austria. And there you get a little bit more detailed information. So that's about the cost. About the cost competition, PV alone, it's not a heating system. You can use it if you use it directly, but then I think regarding CO2 impact, it's quite a disputable way. But if you combine it with a PV system with a heat pump, then you are, I think, more or less in the same range of cost. The issue is what do you compare? Because heat pump is a mixed one. A mixed system. It's not only renewable because you are relying in winter as well on the mix of electricity. And if you go for the solar system, it's as well usually not a pure system, it's a mixed system. So what you see actually is that they are both not yet compatible with a simple gas boiler. But if you start to add CO2 taxes, which might be the most important part to drive it, then there might be a chance to come in the same range of cost.
Thanks for this. And maybe a last question about the cost, but it's more like your views about the cost development for solar, I would say, systems in the future, in the coming years. What would be your expectations in this cost development? Would you see like some cost decrease or increase depending on the solutions? I don't know if you have some guesses about this.
I have some views on that, but it's not that easy to justify. If you look at this cost share, which I have explained that the collector itself, that's not the key question. Yeah. So the topic, and that's the reason why Martin spoke about these simpler tools for planning, that we have quite a high share still in planning. We have a high share in installation, and we have a high share in the cost for selling, for marketing, and this kind of stuff. And whether I think there is a potential for cost reduction, but whether we will achieve it or not, it's not that easy to really forecast. But if there will be a cost reduction, it has to be not in the technology simply. They might be simpler, but it's not the technology themselves. It's the question how to install it. And that's the reason why actually solar heat in district heating, if you have ground-mounted systems in an area where land is cheap, is definitely competitive to other sources with 35 euro per kilowatt hour per megawatt hour.
Thanks for these inputs and your views. Maybe still on your scenarios, some questions about the solar thermal role in the industry. So we saw in your scenarios that industry was considered. So maybe I would say, can you say some words specifically about the industry? Like, is it like how solar thermal can really replace fuel consumptions in the industry, and what could be some I would say solutions to increase this solar heat in the industry field?
Yeah. In our scenarios, we definitely have looked at low temperature solar heat and not fully included in the calculations the process heating. Nevertheless, we tried to derive out of the other calculations to get as well an impact of the solar process heat into industry. But we don't have calculated really the full potential. I think there are better sources within the IEA SHC group regarding this. And that is one of the open questions if you look at scenario analysis, to have really a good understanding of the industry processes. When we started with this, the industry processes were calculated in a quite easy way or simple way, not easy, simple way. And I think that's part of a future work to have a really detailed insight into the industrial processes.
Thanks for this answer. And maybe I would say a last question for Martin. Received the question that we don't have use cases outside of Europe. And I would say from my side, it's maybe simply because no participants outside of Europe were taking part in the tasks. So maybe we can do some promotion about participation in these tasks. But I don't know, Martin, if you would like to say a word about this, the use cases outside of Europe in the compilation of the benchmark.
So you're completely right in your question. As the case study was studied by members of the task, they choose case studies linked to their institute or to the region or to the land of the country where they were living. So in this task, the people were mainly coming from Switzerland, Austria, Germany, Sweden, and Denmark. And it is the reason why the selection of the best case, the best case study was chosen. I think for the survey, which are not the same case study or energy system, it was deliberately decided at the beginning to choose a system only from Austria, Germany, and Sweden and Denmark.
Yes, thanks for these precisions. I think it's time to close this session. I would thank, of course, Martin and Sebastian for these interventions, and I hand over to Joanna.
Yeah, thank you very much, Gabrielle, for moderating this webinar and for taking the questions and answers and guiding us through the agenda. It's been a fantastic webinar. I hope our audience has enjoyed it as well and learned a lot about energy economy and solar heat. So thank you all for joining us. To close up, I'd just like to thank our panelist speakers for sharing their knowledge and expertise today on a voluntary basis. We really appreciate the work that you do and for joining us on this webinar. The next Solar Academy webinar is planned already for March next year, 2018. So we look forward to inviting everybody again to join us for that webinar. We will send you all an invitation end of February, early March. Contact the panelist speakers for further information about what they have presented. Please contact them directly. The presentations will be available on the ISIS website in a few minutes. We're just going to activate that, and then you can see their email addresses. If you use social media, we encourage you to connect with us to continue the discussion and continue to stay tuned to the work of the Solar Academy and ISIS. And last but not least, thank you to our audience for joining us today and for continually joining our webinar series. We appreciate your attendance. You may view the recording in a couple of hours on the ISIS website and also the Solar Academy website. If you have comments or feedback, we welcome you to share this with us so that we can continuously improve these webinars for you. Please participate in the survey that pops up at the end of this webinar, or send your feedback to public.relations@isis.org. I think the only thing left to do is to wish everybody happy holidays, wishing you a peaceful and wonderful end of the year, and all the best for 2018. Thank you very much. I'll close the webinar now.